Hello friends, myself Professor Joshi VM. Today we discuss about the numericals on transformer topic. Okay, let's start the numericals. So, what is a numerical is given, that is a 200 kVA, 330 by 240 volt 50 Hz single phase transformer has 80 turns on secondary winding. Calculate number 1 primary and secondary current on full load. Next, maximum value of flux, and third, number of primary winding turns. So let's start to solve the numerical. So what is the given data? That is, given data is given is kVA rating. kVA rating is given, that is 200 kVA, comma V1 is given, that is 3300 volt. V2 is given 240 volt, and frequency is given 50 Hertz. So we have to solve first primary and secondary current on full load. Number 1, primary and secondary current on of full load. So to calculate this primary and secondary current, we have to use formula of kVA, that is V1 into I1 equals to V2 into I2. Therefore I1 equals to kVA upon V1 equals to 200 into 10 raised to minus 3 upon 3300. After calculating this, we will get 60.6 ampere, that is I1. After that, same procedure is followed for the I2. I2 is equals to kVA upon V2 equals to 200 into 10 raised to minus 3 divided by 240. After calculating this, we will get 833.34 ampere. This is a I2. So we calculate here primary current and secondary current. After that, we have to calculate maximum flux. So to calculate the maximum flux, we know E2 equals to 4.44 phi mf N2. Therefore we know E2, we know F, we know N2. So we will calculate phi m directly. So phi m equals to E2 upon 4.44 into F into N2. By putting the values of E2, F, N2, we will get 240 upon 4.44 into 50 into 80. By calculating this, we will get phi m equals to 13.51 milliweber. Okay, we have to calculate now number of primary turns. Number of primary turns, that is n1. Therefore, n1 upon n2 equals to v1 upon v2. We know that this is the transformation ratio. So, n1 upon n2 equals to, we know the v1 upon v2, 330 upon 240. Therefore, rearranging the terms, we will get n1 equals to 330 upon 240 into 80. So, by calculating this, we will get n1 equals to 110 turns. So we calculate the primary and secondary current on full load, after that maximum value of flux, and third is number of primary winding turns. This is the answer of this numerical. So let's start another numerical. What is the numerical is given? A 20 kVA 330 220 volt 50 Hz single phase transformer has iron loss of 250 watt and copper loss at full load of 410 watt. Find the efficiency of transformer at number 1 full load 0.8 power factor lag, and number 2 is half load at unity power factor. So we have to calculate here full load 0.8 power factor lag, and after that half load at unity power factor. So we have to calculate these. So let's start the answer. First of all, write the given data. Write the given data. What is the given data is given? First of all, given is kVA. Then kVA equals to 20, 330 upon 220 volt. Next, frequency is given, that is F equals to 50 Hertz. After that, iron loss is given, Pi equals to 250 watt. Then PCU full load is also given, equals to 410 watt. So we have to find by this given data. First is full load 0.8 power factor lag, that is n eta FL at 0.8 power factor, number 1, and number 2 eta at half load at power factor, unity power factor means 1. So let's start. Efficiency at full load 0.8 power factor equals to, we know the formula. What is the formula of full load efficiency? Equals to kVA into 10 raised to 3 into power factor upon kVA into 10 raised to minus 3 into power factor plus PI plus PCU full load. So by putting all the values we will get 20 into 10 raised to 3 into 0.8 upon 20 into 10 raised to 3 into 0.8 plus PI is 250 and PCU is 410. So by calculating this we will get 9603 or 96.3% efficiency at full load. So for the second step we have to calculate efficiency at half load at unity power factor. So the formula for PCU at half load equals to 1 upon 4 into PCU at full load equals to 1 upon 4 into 410. After calculating this we will get 102.5 watt. So efficiency at half load equals to 0.5 into kVA into 10 raised to 3 into power factor upon 0.5 into kVA into 10 raised to 3 into power factor plus PI plus PCU. So putting the values we will get 0.5 into 20 into 10 raised to 3 in power factor is 1 divided by 0.5 into 20 into 10 raised to 3 into 1 plus 250 plus 102.5. So after calculating this we will get the answer 0.9659 or 96.59%. It is the efficiency at half load. So here we calculate the efficiency at 0.8 power factor and efficiency at half load at 1, that is unity power factor. Let us discuss one solved numerical. It is a very easy numerical, because of that I solved this numerical. A 200 kVA 330 to 40 volt 50 Hz single phase transformer has 80 turns on secondary winding. Calculate primary and secondary current on full load. Second, maximum value of flux, and third is number of primary winding turns. So what is the given data? The given is kVA rating equals to is 200 kVA, V1 equal to 3300, V2 equals to 240 volt, F is equal to 1500. By primary and secondary current on full load is kVA equals to I1 I2 V1 V2. By using this formula we calculate here I1 and I2. After that maximum flux, that is phi m, this is calculated by using the E2 formula, that is 4.44 phi m F N2. We calculate here maximum flux phi 2. Then number of primary turns, this is calculated by using the transformation ratio. After comparing the transformation ratio, we will get N1 equals to 110 turns. So next numerical is a step-down transformer operates on 50 Hz AC supply with primary voltage of 230 volt. The cross-section area of the core is 50 cm square. So we have to calculate maximum flux Φm, maximum flux density Bm, voltage induced on secondary. Here we have to assume primary and secondary turns to be 500 and 250 respectively. So what is the given data? The given data is E1 equals to 230 volt. Current cross sectional area is 50 centimeter square. Primary turns 500, secondary turns 250. So let us start first maximum flux phi m. So to calculate the maximum flux phi m, we have to use E1 formula, that is 4.44 phi m N1F. After rearranging the formula phi m, and putting the all values, we will get phi m equals to 2.07 milliweber. Next, maximum flux density Bm, that is we have to use Bm formula, that is B equals to phi upon A, but here we have to calculate maximum flux phi m, maximum flux density Bm. So the rearranging the formula will be converted into phi Bm equals to phi m upon A. So by putting all the values, we will get Bm equals to 0.414 Tesla. So third is secondary induced EMF E2. To calculate this E2, we have to use E2 formula, that is E2 equals to 4.44 phi m N2 F. We know all the values, that is phi m, N2 and F. By putting all the values in the equation, we will get E2 equals to 114.83 volt. Okay, I hope you understand all these numericals. So thank you.